welcome everyone. Thank you so much for joining us. So I know we have people here on Zoom with us virtually. We also have this amazing group here in front. All right, so welcome and thank you all so much for joining us virtually and here in person. My name is Jamaica Marshall, and I am very, very pleased to serve as the Shadow the Scientist Programs Manager. Now, you are in for a very, very special treat tonight. So how many of those here and online joining us virtually, how many of you knew that today was International Observe the Moon Night? How many of you knew that? Okay, so I have one person who knew that. All right, so those of you, Victoria, yes, Ms. Newberry online, you knew that. Excellent, excellent. All right, so today is indeed International Observe the Moon Night, and I'm very, very excited to be able to host a special session with you all tonight just for this. Now, we are going to have lunar observing right after this. Is already going on outside. I was hoping to be able to stream it here onto the Zoom, but that's not working for some reason, but it is already set up with Adrienne outside. So feel free to join her there. I'll be out there just a little after 8 and I'll have the moon on the screens so we can talk more and get some nice images there. All right, so our special guest is Patrice Smith, and our session title is Looking for Helium in the Moon's Exosphere. So now get ready. Before we get going, though, let me just say that Shadow the Scientist is an initiative that is brought to you by an amazing team at the University of California, Santa Cruz. And I was so lucky to speak to a couple from the Bay Area earlier. They may have left, but we welcome everyone. All right, so our science guest for this session, as I said, is Patrice Smith. Now, oh, sorry. So someone's asking, is this being recorded in the chat? Yes, this is absolutely being recorded. And the recording will be available online. Yes, it will be available on our YouTube channel. I can post that just afterwards. Okay. Oh, thank you, Adrienne. All right, and so now that we're about to get started, I apologize. Hopefully all right. Yes, all right. Thank you so much. So, Patrice, thank you for being our special science host. And can you please?
Hello. Miss you guys.
It's here. Yes, we love you, Patrice. All right. So, can you give us a quick introduction, starting with not only you're going to be our science expert for tonight, but you were just in Helsinki in Finland speaking about your research that you are doing with the Lunar Reconnaissance Orbiter. So, give us a quick intro and take us into your research, Patrice. Welcome.
Thank you. Sure thing. So I'm Patrice Smith. I'm a graduate student at the University of Texas at San Antonio. My undergraduate was University of Hawaii at Hilo, so nice to hear some friends in the background. Very uplifting. But basically, I've been working on some data on the moon using the Lunar Reconnaissance Orbiter's ultraviolet instrument. It's kind of like a camera. And we'll get into that in a moment. So basically, one of our biggest conferences of the year happened just a couple of weeks ago. It feels like it was yesterday, but it was in Helsinki, Finland. We combined the American Astronomical Association's Division for Planetary Science, if you ever needed a bigger enough mouthful, but basically the majority of the US's planetary division group that usually has its own conference got together with the majority of the European group that usually has its own conference and had this giant, massive joint group get together to check base with each other. So aside from being able to share some of the things we're learning with the spacecraft team that I'm on, I got to hear about a lot of other people's spacecraft teams as they're kind of coming up in all these different countries that are starting to build these different orbiters. So very, very exciting times. And especially exciting tonight. Happy International Observe the Moon Night, everybody. Tonight is really about just connecting with the sky, as many of you I see at the Visitor Center are doing. And we're just going to be talking. Yes. So basically, I'll be going into my research with looking for helium gas around for the most part. But tonight's about everybody just being able to go out and observe the moon in whatever form and shape that means to you. Um, but we kind of, for International Observe the Moon Night, take that word very broadly. This night is picked because it is one of the better nights, weather-wise, conditions-wise, to view the moon from many, many different parts on Earth. So it's meant to be this huge worldwide event for everyone to kind of go out together and have this shared experience. But of course, there are many different, ways of connecting with the sky and nature around us. So definitely we wanted to encourage, in general, connecting with nature in whatever form you feel best in, personally, culturally, however that is. But of course, these days, if you're like me, you've got a device attached to you almost basically 99% of the time. And that is usually what you're looking down at rather than looking up at the sky. And so we also wanted to share just some things that you can go online and look at when you're kind of thinking about what you want to look at the moon at night for, what exact features and that sort of thing. So, for example, these three pictures are pulled from the Lunar Reconnaissance Orbiter's camera system. They have their own website with these really, really fantastic images that they put together over the span of years. Just some of the best images we've had of the moon, and I really, really like these three. The one on the left is a composite image. So they took a bunch of different images and put them together over the span of about a year. And this is the entire near side of the moon. So if it was full moon tonight, and it's almost full moon, the entire near side that you can see, any feature that you see at any point in time here on Earth is somewhere in that left-hand picture. So whatever crater, whatever dark spot, whatever grainy sand, anything you want to take a look at. Um, the one in the middle is more for enhancement for contrast. So you can kind of see a little bit better like the topography. So the deep dark blue spots being those really clear craters in the crater floors, for example. And you can see the rims and white around them as well as higher elevations at a leaving range. So it just gives you a sense of the variation of topography because it's one thing when we're looking at a almost literally black and white image of the moon. And it's another when we're able to see exactly how high some of those mountains and how deep some of those valleys will actually go. But the one on the right, I picked as a reminder to myself to talk a little bit about kind of just the new things that we're going through these days. So it's a little hard to see, but
Uh,
in the center, uh,
Oh, I was going to say we have the images here are beautiful. We can see them here.
okay.
Could you quickly tell us just a bit about the Lunar Reconnaissance Orbiter? How many
Mm,
people here have heard of LRO, the Lunar Reconnaissance Orbiter? So this is an active NASA mission. Can you give us tell us just a tidbit about LRO?
yes, thank you. Yes, so LRO is basically NASA and therefore the US's major lunar orbiter mission. It's been orbiting since 2009. It's got a handful plus of different instruments on board, different tools that were put on to basically assess the moon all in one go. So this was a really interesting case because not only was it a really large scale mission when it first launched, this was the first step to start going back to the moon. The idea of, okay, if we're really thinking about really going back to that era of continuing exploration in the space with humans and things like that, we should really have a good assessment of what this environment so close to us is like. So the different instruments on board the Lunar Reconnaissance Orbiter are made for mapping the moon's temperature at the surface, how deep some of the craters are in its topography very clearly, what kind of ice we see in different craters, what, if anything, would be a good landing spot for a future human mission, for example, now that we have a better idea. It'll be completely different from anything we've had before in Apollo era. So yeah, this is our really, really big lunar mission. And the US has other ones, but usually smaller class missions. LRO is still going to this day. I think, like many NASA missions, it was built for like a year or two, and of course, it's now 16 years old and doing fantastic. And we have more fuel than is expected with being able to conserve fuel over time. And so we look forward to having, some years left of a really, really cool mission time. And I miss state.
Thank you so much for giving us that background on the Lunar Reconnaissance Orbiter. And I did put a link in the chat for everyone to check that out. And let me just say, there are some really cool things that we can find out here at the LRO website, and maybe we'll get back to that a little bit later. Okay, so thank you for that background. I think everyone here is now caught up, Patrice.
Awesome. Thank you. And I did mean to say, please interrupt me at any given time for any kind of question. I'm happy to answer, and feel free to use the chat. I don't know if I have full sight of the chat, so feel free to interrupt me as I go if I miss something, please.
I promise I will. No worries.
Thank you. So this image on the right is kind of, to me, really representative of this really new era of space exploration that we just have not really dealt with before. It's been very interesting for me to see how it plays out. Near the very center of the image, there is this tiny red dot that's a little hard to see, but it is the primary landing site of what was a commercial Japanese lander, a tent, basically. It wasn't able to successfully land, and like many other commercial landing attempts, crashed as well. So far, I think we've only had one that successfully stood up the way it was supposed to, but with LRO, aside from observing things like craters and looking for geological features on the moon, now is also being used to change its orbit and to observe these other new landers from our country and many others, to observe their impact and what kind of gases they're releasing, for example, with their rocket exhausts. And it's just a totally different type of science. So, connecting to the moon tonight applies in many, many different ways. Um, there we go. I like to point out this area though, and I'm sure you will later on. So when I'm observing the moon, and whether or not I have binoculars or a telescope or just my own eye, without my glasses, at least I can see the left dark spots very, very clearly because of how large they are, and how much they're in contrast with kind of the really, really bright, high reflective areas sort of below it, for example. So these area are called Maria. See, it often spelled as Maria, but these Mariae, which was meant to mean seas because it looks like these dark, like seas or lakes or oceans on the surface. These are kind of just really old lava flows, basically, from impactors or otherwise. So, and for example, there's one at the top left there called Mare Imbrium. And you can see just how large that circle is. So this is one impactor from billions of years ago that was a part of the heavy bombardment period. So when the solar system was still settling down is what the estimated time was. And so you can see just how large scale these impacts were and just how much they could melt rock around them. And then you've got really large areas like Oceanus Vocalarium, however you like to say it, where there's been so many other impactors and so many melt spots that it just takes over this whole area of just like dark basaltic rock. As many of you have seen, basically being on the side of Mauna Kea, this sort of really dark rock that you see that's produced from things like volcanoes. So these are at least features that you can see with the unaided eye. And in particular, there are two bright spots we'll be able to see tonight that are craters that are pretty interesting. One being in the middle of the Mare, so Copernicus. I'd like to see just, the fact that it's over the dark spot, you can tell it's a little bit younger. And so these are sort of younger impactors, but Tycho in particular, Tycho, its striations stretch so far beyond where its impactor originally is. You can see that tiny circle, but then you can kind of follow how long those lines are, where the ejecta pattern was very large. So we've got all these cool things that we can see tonight. We're not quite at full moon. We've still got a terminator going on, which in my opinion is like kind of one of the best times because when you have this dark side edge of the moon, you get this really nice contrast along that line, along that limb, and you can see really well these different features. So Oceanus Maclarium and Tycho should pop really, really well tonight.
Definitely.
But I'm sure many of you.
I was just going to say, so we actually have lunar observing happening here live right outside at the Viz. Adrian is running that. I was hoping to stream that here, but I have 4 devices going into Zoom right now, and it's just not letting this other one join. So so we actually can see those outside right now. And you said that the mare are basically old lava flows. Now, is this from the formation of the moon or from
Mm,
impactors?
mostly impactors, exactly. I'm sure there's debate over how much is left over from the original impactor of I believe it's Thea, or Thea is what it was called, sort of this protoplanet that was thought to have crashed and collided with the Earth, early Earth at some point and sort of formed. But we don't see those dark spots on the far side. So I think that's part of what keeps it in my mind as like, okay, I wonder how much of these lava flows were coming from that early era of that, having that impactor, since it's on the side that's closest to the Earth. And you just have these really, really, really big mare regions. But yes, most of them are from just enormous impactors that were able to deliver enough energy to melt the entire surface around it. So pretty incredible.
Thank you, Patrice. All right, now we have some questions in the chat. Those of you joining me virtually, please continue to drop those questions and comments in the chat. Those of you here in front of me at the visitor station here in Mauna Kea, you can just come on over and ask your question. All right, so our first question is from Vani. Vani says, what can the moon tell us, she asks, what can the moon tell us about the history of the solar system, Patrice?
Ooh, that's a good one. So its bombardment tells us something that the Earth could not. And I think this has been a more interesting subject as time goes by over the last few years. So as I'm sure they might be alluding to, the Earth doesn't really reserve its previous impactor craters because we have so much erosion going on. We've got wind that kind of erodes the surface over time, let alone vegetation, let alone the atmosphere, let alone water, and for the recycling of our Earth's crust. So we really don't have old surfaces to the point of being able to date back craters so long ago. Versus the moon doesn't have this atmosphere, it doesn't have these enormous beds of water to sort of rub at the surface over time. And so in this case, we're able to see just how uh, active our region around us in space was in previous times. Most of these craters date back billions of years ago. So it basically teaches us a little bit about how active the early solar system was with things like asteroids and protoplanets and comets and that sort of thing. Yeah, it's a good question.
Thank you. Great questions. Okay, so we have our second question. Oh, yes. Now, could there be ice or water ice beneath the surface of the moon? And I believe we
Mm.
already know that there is water trapped in ice form in maybe the southern polar region.
Exactly. Yes, definitely at the poles, but especially the South Pole has been of interest in particular. It looks like when we do send our manned missions back to the moon, that's where they'll go. Partially being there's a lot of water in that area for them to be able to use. But I do find the idea of just exactly how far you have to dig to get to more and more sort of frozen patches of water really, really interesting. As I mentioned earlier, you do have a lot of commercial missions going out, but there are some non-commercial missions that are interested in studying the surface and just beneath the surface. It kind of comes with its own problems, one being the regolith or the dirt, you could say, of the moon is extremely variable. Having, for example, lander, one of the reasons we don't have a rover usually going on the moon, is the fineness of that, the grains of dirt usually get in between the tiniest crevices of any kind of mechanical object and shred it to pieces over time pretty quickly. So yes, I think when we do send our next batch of human astronauts to the moon again, it would be nice for one of them to bring a shovel. That would be kind of cool.
That would be very cool. All right, keep those questions coming in the chat. Those of you here, if you have questions, please come on over and ask them. So scientists think that the moon and the earth are very closely related. Now, you mentioned Theia earlier. Can you tell us about Theia and how it connects to the formation of the moon?
Yes. So it's thought that the moon is basically made from one very large impactor. There have been a lot of studies over whether or not it might be one or it might be several, and it looks like simulation-wise, it looks like the most likely case is one enormous Mars-sized, basically planet running into the early Earth protoplanet. Some exchange of materials would have had to happen because, as far as I guess geologists are concerned, a lot of the rock of the moon is very, very close to the composition of Earth, even if it shows up as differently as it does. So yes, that is a good yes. We are. It seems we're still on the Theia hypothesis for sure. Now the papers I've seen mostly lately are on whether or not it was one impactor that then just bounced off and then got locked into orbit, or if there was some kind of change where it might have been, going around and then it or wasn't tidally locked for a while, that sort of thing.
Brilliant. Okay, so we're getting more questions. And this one is from Ms. Victoria Newberry. And thank you everyone at the Akaula School on Molokai for joining us. We're so very happy to have you. And let me also just take this opportunity to welcome everyone that we have here. We have Annalise joining us from South Africa. Of course, our science host, Ms. Patrice Smith, here from the University of Texas at San Antonio. We have Daniel, Julian, Nikki, Ms. Peggy Lamont. Welcome, Ms. Peggy. Renee, welcome. Rob, it's always wonderful to have you. Ms. Newberry, so happy you can make it. Vonnie and Miss Yuli Preston, over on Oahu in Honolulu, at the Dole Middle School. So welcome to everyone. Okay, now another question. This question is from Miss Newberry at the Akaula School. Okay, so first, Ms. Newberry asks, can you describe how lava flows happen from an impactor? So say we have,
Mm,
a small size, medium sized boulder coming towards the moon, and then it impacts. How does that create lava?
that is a great point because I think what's in that is the fact that space is very cold, and so you do get this instant freezing, basically, of what would be a lava surface, but it just freezes very quickly. But basically, they've been able to simulate this in the case of the moon and other solar system bodies, but you can usually estimate the size of the impactor based off of the size of the crater it makes, basically. But these are ones that are coming in at enough speed where their energy would basically have to transfer. So going from, what would you say? Your kinetic energy comes to a slam, right? And so something has to absorb all of that heat and all of that energy, and a lot of it comes in the form of heat, melting the surface. But yes, to the point I think that's being made, how exactly, how long or in the sense are these lava flows flowing? Yes, I do think they would be basically frozen pretty instantly.
Okay, so hopefully that answered your question. If not, just put a follow-up in the chat for me. These are great questions. Okay, we have another question. So can you describe the differences between a lunar eclipse and a solar eclipse?
Mm, okay. So a solar eclipse is when basically the moon gets kind of in front of the sun from our perspective here on Earth. And I'm sure I'm going to be mixing up the terms. Jamaica, you probably know the terms better. One of them's the umbra, one of them's the penumbra. But it depends on the position the moon is in at that point. Whereas on the case of a lunar eclipse, for example, which I actually have a picture of one I'll show in a bit, but basically you're dealing with just the moon being in one part of the shadow, not in front of the sun exactly. Yeah. And that's when a lot of the time we get our blood moons. We just had one recently, in fact, because the light being reflected off of the moon is then kind of overshadowed, and so it scatters differently, and we see it usually a little bit more red, just by nature. But
I see. So you said you were going to maybe show us an image of that?
yes. Mhm. Yeah.
Please do, please do.
Okay.
And while Patrice is going to that image, those of you who are here and also in the chat, thank you for the great questions and comments. Please keep them coming.
I didn't
Oh,
realize it was the next slide, so that's perfect.
oh, wow, that's beautiful.
This is in Helsinki on the left, or excuse me, on the right. It was in Helsinki. Sure enough, they scheduled, as nerdy as it is, they scheduled the conference. The first day you get there, it was the lunar eclipse. Just the perfect nerdiness that we had there. So I was walking with my colleagues that just gotten off our long flights, and we were walking around the town and went, "Oh, there it is. Okay, it's already." It was ending by the time we got a good picture of it. But there you can see, for one, the redness, but you can also see on the left side exactly how bright that brightness is in contrast. But yeah, yeah. So part of the other reason why I put these photos in here was to basically kind of elaborate a little bit more on the general idea of observing. I'm so glad so many of you guys got to go up to the mountain tonight and have that great experience. The sky is like nothing else. And so here in San Antonio, in the middle of a city of a couple million people, with light pollution, I gotta kind of take what I can get. So the picture on the left was an image that I saw. I was driving near the airport and I actually pulled over, and you can probably see the Southwest sign at the bottom right corner. But basically, it stood out to me to a certain degree of going, okay, I haven't seen the moon this clearly in a long time. We've got, aside from light pollution, regular pollution. So I pulled over, probably interrupted traffic when I shouldn't have. But it was a great view, and having that moment of going, oh wow, I haven't seen the moon this clearly for one reason or another, and I don't know how long. That I'll call observing as well.
That is
Mhm.
absolutely stunning, stunning. Thank you so much for sharing those. And we have more questions. We have 4 questions here, 2 from our audience here at the Visitor Information Station on Mauna Kea. So, first question is, and this is from Ms. Vani in our virtual audience. Does evidence show that people may ever be able to live on the moon?
Mhm.
Because I know
Well,
we're trying to get there. We want to have basis. Can we do it, Patrice?
oh, I have opinions. I have opinions, and I'd love to hear yours as well because I'm sure you have some. Um, One way that it was put that I thought was a really good way of describing exactly how seriously problematic it is to try to maintain a human presence. Maintaining a base is one thing, maintaining a human presence is another. Is a lot of the time it's compared to really old days of traveling and discovering different islands and having to start from scratch and collect your resources. But the joke is always that back when we were still kind of separated in our different places, traveling around, you might not have known the area, but you still had trees to cut down. You still had, streams of water versus here. You're not really, in the case of the moon, you're not really dealing with that sort of thing where you can find, for example, just like wildly growing vegetables anywhere. Everything has to be kind of dragged up from Earth. And every time you have to pull something up from Earth, I say pull because the amount of energy of fuel really that it takes to get certain kilograms amount of weight off of the surface. It's a lot of fuel and it's a lot of money. And so that's part of what's driving this search for resources is because as much resource as you can find will save the taxpayer costs in the long run, especially in the case of water, for example, our primary thing that we will always need no matter what. So yeah, I feel like it'll be difficult. I'm sure you could do it if you were willing to spend an enormous amount of money. But at least for having a base, and every once in a while being able to send up astronauts, I think we're getting there. We're a couple of years behind in our Artemis program, but we're getting there, definitely getting there.
That sounds hopeful, Patrice, and I appreciate how hopeful and positive you sound about this. And that's a great segue into a question, our first question from our Viz audience here at the Visitor Information Station on Mauna Kea. Could you please speak a bit about your research and specifically helium in the atmosphere? Now, in the atmosphere of the moon. Now, we're talking about helium-3, right? Which is a really rare isotope, am I right?
In our case, I think we only pick up helium-4, but to your
Ah,
point, that's exactly right. That's exactly right. Is helium-3 is the other thing. Helium-3 and rare earth elements apparently are the things that we really need to get a hold of on where exactly we see it on the moon. So I definitely think there's going to be a new area of research for sure. Thank you for pointing that out because I think that is a really important note. Um, yes, so I guess I'll start with this slide. I basically just use light or spectra. So I like this diagram from Noir Lab that I borrowed. But basically, it's taking the example of having a source of light. It could be a star, could be a light bulb, any kind of source of light. At the very left side bottom, it shows that if you were to take white light and disperse it into through a prism or any kind of dispersing element, you see a rainbow. And basically, when white light or any other group of light is passing through other things, this when you start to get kind of differences in exactly what you're picking up. So in the case of the cloud of gas in the middle, top middle there, when the light is coming through the top middle all the way to the right, we see that in that rainbow, it starts suddenly missing very specific colors, like a very, very specific color of fuchsia, very, very specific color of purple, very specific color of blue, and that sort of thing, and orange. And so these are what we call absorption features, which tells us that there's something in the gas that is absorbing exactly that type of light. And that type of light being a very specific, we call it a wavelength. Light is just electromagnetic waves. And so all photons, in a sense, you can think of, have this sort of size or this wavelength. And that's what kind of determines the way we perceive its color. And so when we see missing colors in a continuous source, it tells us, okay, there's something that gas is made up of that is absorbing that light. And if we know what types of gas eat those types of colors, is what one way you can think of it, then we know what that gas is made out of. And then the other, which is what we actually do in my case, is we use emission spectra. So at the very center bottom, it's actually the opposite case. So if we were just looking through the gas, for example, without looking through the light source, that gas is gas, so it's got a lot of particles swirling around basically, and any kind of particles moving or changing their energy states. And so they emit certain types of light. And I like to think of it in terms of, like, for example, neon, literally and figuratively. Neon signs, for example, they're very, very specific, sharp, bright colors. The green and the red, for example, they're very specific light emitters because of that gas that's inside of them. And so in my case, emission spectra is what I end up looking for. So each species kind of has their own colors that it takes in. It's based off of the way that the atom is set up in terms of how many neutrons and protons and electrons it has, for example, and what kind of state the atom's in, meaning where the electrons are in its orbital states. All it really ends up meaning is basically they absorb or emit extremely specific types of light and only those extremely specific types of light. So over many, many years, people have done basically a lot of the periodic table to see, okay, if we're missing certain types of light or if we're getting emission in the spectra of certain types of light, what wavelengths, what size of light is that we can associate with that element? And so this is an example with helium near the range of what is for us visible light, basically. So this is a representative case where the purple on the left bottom is actually purple. So there is an emission feature of an active helium atom, for example, at 388 nanometers, that sort of thing.
Is this helium-4?
Helium-4, yes, I think
Okay.
so.
So what's the difference between helium-4 and helium-3?
Just an extra neutron. I'm not quite sure technology-wise outside of astronomy, to be honest, what exactly we use for helium-3. I'm sure others know that are a part of this or in the room even. But as you know, in astronomy, a lot of the time we need to cool down our detectors, and you can mix helium-3 and helium-4 in very specific ways and really extract a lot of heat out of the system to cool down an instrument, for example. Yeah.
Brilliant. Okay, so our next question from our Viz audience here. Um, why did we stop going to the moon? Why haven't we been back? I know we have plans to go back soon-ish, maybe, but why did we stop?
Fair enough. I think your whatever your answer is your opinion is as valid as mine because it still baffles me to this day. To be fair, the space shuttle program had reached a pretty good pinnacle, is my understanding of it, and there was going to be a gap between because that's kind of when around the time you and I were in school. There was going to be a gap between the end of the space shuttle era and beginning of some of the next level powerful rockets. The SLS, for example, was kind of that next upgrade and exactly how much thrust power you can get for to go into space. So I can definitely see there being a break in terms of going, okay, we've gone to the moon, we've figured out space travel, we feel like we've gotten it down, we have people in the ISS. Okay, cool. Maybe we'll figure out what we want to do later. But of course, the moment other countries are like, hey, we're going back to the moon, suddenly we're like, okay, us too.
That's right, and I feel like
um,
that's what's happening right now.
yeah,
We have a moon race in our hands for sure.
exactly,
That
exactly.
again. All right. So we're heading back. We're heading back. That's the
Yeah.
answer there. We're heading back. Okay. So um um from Miss Newberry here, are there any rare or valuable minerals on the moon? Now we were just talking about, you're talking about helium-4, helium-3 I know is really appealing industry wise because it can help have for clean energy for uh,
Oh, okay.
yes. And in fact, I was just listening to a podcast. I forget the name of this company, but they're hoping to start doing some capturing of helium on the moon, maybe in the next
Yeah.
4 or 5 years. And yeah, I'm looking at
Mm,
my notes here that helium-3, in theory, could not only be used for nuclear fusion, but also when we talk about fuel, just in
mm,
general, if we have a lunar base. So we know helium-3 is something rare on the moon. What other
mm,
rare or valuable minerals can be found there, Patrice?
mhm. Um, so I know there are a lot of rare earth elements that go into basically things like our electronics, cell phones, microchips, things like that. Um, in particular, there's something on the moon called creep, which is a very funny word for it, but it's KREEP, potassium, the K, REE, rare earth elements, and P. Do I have it backwards?
Wait, can you
Potassium
put that in the chat for
and
us? Potassium?
yes, thank you. I hope I'm not mixing up my
Creep.
table of
Okay,
elements.
creep.
Yeah,
Okay.
creep with a K. Um, Potassium P. Sorry, thank you guys. Um, but yes, these are basically areas where there was a spacecraft in the, I don't want to get the year wrong. Whatever it was, the photos that I saw from it were in black and white, if that helps. But basically, there was a spacecraft early on that had a gamma ray spectrometer on it. And I learned this kind of recently, just about a year ago. But basically, it was able to pick up sort of where the creep terrains were. So these areas that have the things like potassium and rare earth elements and so on and so forth. But in particular, uh, thorium, uranium, what's the other one? I know radon's been detected. But more so, they were more interested, at least at that time, in it for the geology perspective. As far as I understand, there's something about using those elements to kind of associate either with age or with volcanic activity, the parts of the moon that you're looking at. Yeah.
Thank you. So sorry, we're having lots of conversations here at the visitor
Okay.
station. And so to continue this, we have a follow-up question here about the moon, sorry, about extracting the water in the southern ice cap from the moon, and how
Mm,
can we use that to create fuel there if once we do have a human base?
mhm. This is something particularly relevant, as you know, with projects. There was a project based in Hawaii that was looking into this, but basically, one of two of our major fuel sources when we're launching things into space, and eventually when we start launching things back, are oxygen fuel and hydrogen fuel. So the idea is, aside from being able to find water, which is good for us as far as maintaining a human presence, eventually, if you wanted to, for example, use the moon to be a almost a rest stop to then go and launch from the moon to something like Mars, for example, then you would want something where you could break apart that H2O or OH and get oxygen and hydrogen and use those as fuels independently. Yeah.
Perfect. Thank you. Thank you. All right. I think that's all the questions for now.
All right. Okay. Well, I think I'm just about near the end of my slides before I kind of hop into the nitty gritty of the research. Yes, I think this is, I'm just about. So I just wanted to point out really quickly, especially for International Observe the Moon Night, we've got our telescopes that we use, for example, at like the visitor station, and then you've also got ground-based telescopes and observatories, like for example, at the top of Mauna Kea, places like Chile, that basically once you get above that enormous layer of water and big chunk of the atmosphere, you can really do some good observations. But in particular, the project that I work on requires a different level of getting out of the atmosphere. So in my case, I use the lunar orbiter set of data because the light that I'm looking in is actually ultraviolet. Nicely enough, our atmosphere blocks out a good chunk of ultraviolet light. That's good for us. But if you're trying to observe how something glows in the ultraviolet, for example, helium has a very clear ultraviolet spectrum, and other things have very good emission in the ultraviolet. You would want something that can basically not be affected by the atmosphere, where it's all getting absorbed and you're not getting any light basically from that range. So yeah, that's what I end up using. I'm going to go into a very nitty gritty of exactly what we're using from the Lunar Reconnaissance Orbiter. Any more questions so far?
Well, you've already answered 13 questions, so I don't have
Wonderful.
any. I don't have any. I don't have any right now. But
Good,
I'm
good, good.
sure we'll get. Oh, sorry.
Mhm.
Did I miss one? Yes. Okay, I did
Mhm.
miss the question. I'm sorry about that, and I will reshare it here.
Oh,
What's the
thank you.
main goal of LRO?
Oh, good question. It has several goals, all of which have actually been met, and so now the missions, the mission has kind of redefined itself. But basically, the goal was to have an extremely good idea of the behavior, the form, the shape of the moon. So that includes, for one, topography. So this part of the goal was to map. There's a laser altimeter on board, and basically that maps with high accuracy exactly the slopes, the crater bottoms. So that picture we looked at earlier, where we could see that altitude map, that's what that came from. What are its highest peaks? Where are its highest peaks? Let's get the best maps possible. How is its temperature? How's the moon's temperature varying over time? What spots absorb more than others? What exact minerals are we seeing where? This was just one giant sweet set to just do all simultaneous observations continuously in orbit. and get as much information as possible from that. And so we've now extended that a little bit more where we're able to do a little bit more science in other ways. For example, sometimes we slew and observe things like comets. And so there's a lot of other science that is done in addition now these days. But yeah.
Yes, wonderful. Okay, so we've been in the background. I have the Lunar Reconnaissance Orbiter page pulled up, and there's a lot of resources there. And I really want to point them out because one of the goals of International Observe the Moon Night is to raise people's awareness about the moon. And also just to have better understanding of the science, lunar science, and also connect that with our cultural stories and our personal
Mhm.
stories, art as well. All of
Mhm.
those things come together, and one way to really see that is in this visual, which I'm going to share my screen if that's okay,
Okay.
Patrice.
Yeah, I'm
LRO
stuck.
has, so I'm just going to go here now. I've already put this link in the chat. But so I'm here on the LRO website, and there's so much interactivity here that I really want to make
Mhm.
sure that people get the opportunity to see this, and hopefully they can check it out on their own. But let's see, you can search for things with this interactive software. So if I put in the Lunar Reconnaissance Orbiter, there it's showing me
Oh,
exactly
very
where,
good.
yeah, showing me exactly where it
Mhm.
is. Now, I believe before that you have done some programming and actually told the spacecraft where to go. Can you tell us a little bit about that?
I did my best, yes. Thank you. Yes, so basically, every once in a while, we actually have to change, adjust a little bit where we don't change the orbit, but we do kind of slew a little bit and turn to calibrate. As you know, and as many of the people who are related to working up on the top of the mountain know, to get your data properly calibrated and to make sure you're getting rid of any kind of extra signal that's not real, one of the things that you have to do is you have to test your detector regularly. It's kind of almost like a camera, and you test every pixel of it basically when you take this long image of it to see some pixels are going to be more sensitive than others. And so you don't want your weights of the light that you're measuring to be off. So you have to measure that every now and again because your detector is going to change over time. And so usually that would be done by like if you're at a telescope, for example, in Mauna Kea, some might, for example, close the aperture. You can think of it as closing the peephole or putting the cover over the camera and then taking a picture and
Oh,
seeing, if there's any bright spots or, anything like that, and then you calibrate it out basically.
yes.
You can't do that. So the way that we get around it is we have to ask every now and again and say, hey, can you turn us to a star that we know really, really, really well? And
Mhm.
so there are stars that peak in lights that are more intense than ours. So, for example, our sun peaks in visible light, what we're used to, but some stars peak in ultraviolet light. And those are usually the very blue stars that you'll see in the sky. And so anyone that we can find that there's a couple that we use that are pretty stable stars where we know their spectra very, very well, and we're able to point and observe that for a short period of time to basically make sure our detector is behaving the way we expect as a check. So yes, to do that, you kind of have to send in a little short piece of code and hope that you get the code right, saying, "Hey, can you please, turn the spacecraft this way, point it at this star, move a little bit, stare at it for maybe 5 minutes, and then turn back onto the moon." And if the code doesn't go well, the detector will kind of shut itself down just to protect itself, just in case.
Uh-oh.
And so that, yeah, so that's happened a couple of times, but we got it down now.
Whoops. All right. Wow. I mean, I can't imagine how much pressure that is when you're writing code for millions dollars of spacecraft there, but you get to do this, and you're working with a professor at UT UT San Antonio. How can we keep up with your work, Patrice? Because you're talking about your most recent research there in Helsinki, in Finland, and we're hoping that this will continue. So, where can we find more of your work?
Technically, we're a weird program that works out very well. For those who are familiar with the UH Manoa and IFA circumstance, we have a similar one where
Mm,
UT San Antonio partners with something called the Southwest Research Institute. They're known for a lot of different technology things, and
that's
there's a lot
right.
of buildings I'm not allowed to go into. But they do have their own space sector that they participate in a lot of spacecraft missions, a lot of NASA missions, basically. And so my professor, basically, that I work for, is dual employed by Southwest Research Institute and UTSA. So he has gotten to build some multiple instruments at Southwest Research Institute. Yeah.
Incredible, incredible. All right, so we have another question in the chat. Vonnie asks, "What role does the Lunar Reconnaissance Orbiter play in the success of the Artemis program?" Assuming Eleanor will
Mm,
still be there, I can imagine that collaboration would be really productive.
right. I appreciate that question because that's something that is something that needs to be worked out at some point in the next few years. So basically, the Artemis program, we have gotten done with Artemis 1, where we sent an unmanned spacecraft to exit the Earth, orbit around the moon, come back around the moon, and then skip off of the Earth's atmosphere to dump some momentum and energy, and then land into the ocean. That went relatively successful. And in fact, it turns out our rockets are powerful enough these days where it shortens the time. So it used to be about 4.5 days for us to get out of the Earth's atmosphere, go to the moon and back. And I think they did it in like 3.5 this time around. So that's something very interesting. Artemis 2 is supposed to be our crewed mission. So we have the 4 astronauts that have been picked. They were picked some years ago, and I like to follow them because they do crazy training, and every now once in a while, if you follow their social media, they're posting about hiking on whatever it is, K2 or whatever, and it's just their weekend fun basically. And a couple, if not, the goal is for the end of next year right now. I think that's the goalpost right now, for them to basically go into that spacecraft and orbit the moon. So that'll be Artemis 2. Artemis 3 is when we actually land humans onto the moon, onto the surface again. So that'll be some year. We've got a couple of years before that. But we've planned through a few. We were through Artemis 4, I believe, which is like collecting more samples, establishing more base, that sort of thing. And the main idea behind whether or not you would what you would want from LRO being involved in the Artemis missions is, aside from making these maps of, like you were mentioning earlier, the South Pole, you would want something that can ideally watch over the astronauts as it's in orbit. And so even if LRO one day runs out of gas sooner than the Artemis program is ended, hopefully we'd have a successor basically go up. I see you got the stream up. Looks great.
again. Yes. So no, my question was, can you leave us with one really amazing fact about the moon as we wrap up? And those of us who are here in person with me, we already have our live imaging going on outside with of the moon. Ms. Adrian is taking care of that. Give us one of your most amazing facts about the moon to close us out. This has been a really, really interesting session.
I'll go with um, I'll go with its size. Relative to any other moon planet ratio, our moon has one of the largest sizes compared
Oh,
to the planet that it is assigned to. And it is suspected that that is related to our ability to live and host life here on Earth. So it's possible that the moon plays a really big role in our habitability. I think that's really interesting.
I didn't know that. I think we're going to have you back again, Patrice,
Oh,
to talk more about how the formation of the moon and having the moon as a part of our system here actually helps with habitability of Earth. That's quite something. Let me just check the chat really quick to make sure we don't have any more questions. Oh, and we do. Yes. Okay. And so the question here is, and we feel free to just give us your own personal answer here. But
okay.
the question is, do you think the next Artemis mission is going to go ahead?
I do. Um,
All right, good.
yes, yes, I do. I do. And I think we're past the point of getting too many more pushbacks. We were supposed to go, I think last year, maybe 2024. So this is our second delay, and I'm hoping this will be our last. But if not, it's very close to our last, I think. I think.
All right. Well, I'm really glad to end on such a high note.